All right. Today is going to be another pencil and paper day. You'll find that most days in class we're going to be working through concepts with tablets, pencil and paper. So you don't need your laptop. That'll be fine. And today we're going to be practicing conditionals and picking up where we left off on Tuesday. Couple of quick announcements. This is the same announcement as was made on Tuesday, but now that Quiz Zero scores are out, I want to remind you to please review your work. These concepts are important to understand. Some of the most commonly missed questions were about function call ordering and the way that function calls evaluate, confusion between print and return. If you're confused about anything on that quiz, please come work with us in office hours, ask conceptual questions, try and talk the TAs through the questions that you missed. And that's the best way to come to a full conceptual understanding, right? We're going to continue building on those concepts. They're not going to go away. In fact, you'll see today that we're going to be diving in even deeper. So we're going to start with turning it to you all and going ahead and following a function that makes use of conditionals, as we talked about. There's some if statements here. And work with your neighbor, and I would encourage, you can think through this first without diagramming, but this might be a good one to try diagramming as well. Let's spend 5 minutes on this. The TAs will be circulating around to help you with this. If you have any questions on if statements. One more minute on this. One more minute. Twenty more seconds, and then we'll talk through this. 20 more seconds. All right, let's give this a go. So, as a warm-up, we're seeing a function definition, and in it we're seeing the simple form of an if statement, right? We've got 3 independent if statements. Some of them have return, some of them have prints. In order to know what this is going to evaluate to, we have to trace through it very carefully. All right, so I've gone ahead and fast forwarded to the point of reaching line number 15. Let me try and find a color that works in both sides of this real quick. It kind of does. All right, we've reached line 15. We see that this is a print statement. We need to figure out what does the expression inside the print statement evaluate to. We've got called a foo. The argument x is assigned -1, so we're going to set up a frame for foo. X is going to have a value of -1, and the return address, we always have to keep track of that, is line 15. So that's where we'll go back to, and whenever we come back with a return value, we'll know what to print here. I want to remind you all, this was another common misconception on the quiz, the difference between the return address and the return value. So RA, or the return address, is the line number, in this case line number 15, that a function call is evaluated on. Once this function has finished evaluating, once it's reached a return statement, that's when we'll know what to fill in the RV, the return value, and where to send back to the return address, the RA. All right, so let's jump in. So x is -1, and we reach a test. Is x equal to 0? No. So we skip over the return x plus 1, and we continue on. Is x equal to 1? No, right? So we skip over this print statement, and we continue on. Is x greater than 0? No, it's -1. So we skip over this return, and we reach line 12, and we are returning x. When we reach a return statement, remember we substitute in, or we need to fully evaluate the expression of the return statement. In this case, it's just look up x. So we look in we use name resolution. We ask in our current frame, do we have something named x? Yes, we do. Its value is -1, so -1 is going to be our return value. Our return value is -1. We send that back to line 15. And so -1 is what's going to be printed first. Right? Any questions on the evaluation of the foo call on line 15 moving forward? The next one's a little bit more interesting. So we've reached this point in our program, and we're back at line 15. We just completed it, but this is one of those cases where there's another line after this. So that's okay. The computer's going to continue on, go to the next thing. And the next thing is another print statement, same type of function call, but notice that the argument x is changing to be 1. So we run through the same set of steps. We set up another frame for foo. This time, notice the return address is the line 16, because that's where this function call is originating. X is 1 this time around, and we're ready to jump into this function. So we ask, is x equal to 0? No, it's not, right? Then we ask, is x equal to 1? Yes, it is. And here we print something you just read about, a format string or an F string, right? And so here, now that we've got format strings in our repertoire, it actually winds up being much more convenient and useful and pragmatic to use rather than concatenation. If we had concatenated this string, so let's recall what this is going to do. So we're going to take, so an F string begins with the letter F, and then is followed by quotes. So that's how you know it's an F string versus a normal string. And the special capability of an F string is we can use these curly braces inside, right? So these curly braces here to write an expression. And notice this expression is taking an int value, subtracting 1 from it. So our current value of x is 1, 1 minus 1 is 0. So what this is going to do is it's going to substitute 0 between these curly braces, and it will fully substitute those curly braces, right? So our printed output here is going to be x colon 0. Right? Maybe I'll put a slash through that 0. And that's great. If we had needed to do concatenation here, we would have not only needed to say, you know, x colon space end quote, concatenate, and then we would needed to convert to a string x minus 1, right? We would have had to call stir x minus 1, and it's a little bit more verbose and clunky. Now that we understand F strings, we'll tend to favor these because they read more easily once you're used to the syntax. But behind the scenes, this is doing concatenation. It's just a nicer way of doing it from the programmer's point of view, all right? So we're not done yet. We've just printed some output here on line 7. Before I continue on past this point to line 8 and 9, any questions on F strings or what we're seeing here? All right, all right. So we continue to line 9. We reach if x is greater than 0. Well, x is 1, right? We look in our current frame. Our current frame is the lowest on our stack that hasn't returned. X is 1, and 1 is greater than 0. That's true. So we go into the then block, and we return x multiplied by 2. So we figure out x is 1, 1 times 2 is 2, so we enter our return value. This function's job is done. The return value is 2. We send that back to line 16, right? We don't continue on. As soon as you evaluate a return statement in a function definition, you're sending that return value back, and you ignore anything else that comes after it. And we would print that value. So we're printing the return value, which was 2. And that would be how this one rounds out. Questions on this evaluation? So we didn't see any else branches here. We will see some else's today. Yep, question. Why is the return value not x colon 0? Good question. So let me back up just a minute here, and we're going to go back to the point of this print statement. All right. So I've rewound time, and we're at line 7, right? A key understanding of print is that all it's doing is sending some output to the screen. So if you're running this in Trailhead, you would see a new line of text output in your screen. And what it's outputting is whatever is inside of that expression, right? This is just an expression that's going to generate a string of output. And this is where we would see, you know, x colon 0 produced to output. Oh, and I forgot, I didn't mean to remove x here, so x is still 1. All right, so once this line is completed, this is what would show up on our screen. But what's going on in our program and the evaluation of this is going to continue forward, right? And so we continue this if statement. And notice that in our current frame, where we care about what is x currently, what is x's value, x's value is 1 still. We didn't change anything about x in order to print that output. We just did a little bit of arithmetic and didn't reassign x in any way. In fact, we haven't even learned about reassignment. We'll talk about that later in the semester. So x is still 1. We haven't changed anything about that in our current frame. And when we reach the return statement, this is the key point at which you realize, okay, this is what this function call is going to evaluate to. And so 2 here is going to be sent back to line 16, the return address where this call occurred. And that's why we would fill in just 2, because 1 times 2 is 2. And then that would get printed out on line 16, and that's how it would finish up. Does that help? All right, cool. Other questions on this? Yep.
So if x is greater than 0 statement wasn't there, then it would automatically go to the return x, right? So would the return value have been 0 then?
Great question. If we imagine the same function call for a moment, but we elided or we removed this conditional, and we reached return x. In this, we would look in our current frame, and we would see that x is still 1, and we would have returned 1 here, right? So when we printed, x is x minus 1, this didn't change anything about x. It was just a computation that was done in order to produce this little bit of output.
So return is changing the x value then?
Return isn't changing the x value either. Return is just going to look up in my current frame of what I know x to mean in this moment. What is x's value? It's 1, and so we're going to return that back to the sender. Yeah. We will learn later how to change variables' values, but for now we're going to assume that within a function call, a parameter's value stays the same for the time being. Yep.
If you didn't want the x minus 1 within the curly braces to be evaluated, how would you change the f?
If we didn't want x minus 1 to be evaluated, so you mean you just want to print like the string x minus 1 literally, or?
X colon like
Just x?
1 minus 1.
So we could have, this is just an expression here, so you could write any arithmetic. So we could have done 1 minus 1 if we wanted to. We could have just had x here, and it would have printed x as 1. So between these curly braces, so if I have f quote x, and then curly brace x, that would have printed x colon 1 here. So between these curly braces, this is, and actually this is a good note to make, because this fundamentally gets to the point. Let me see if I can, I'm going to switch over to somewhere else and get to a blank. So what I want you all to appreciate here is that if we have a value x, and let's say its value is 1, what we've known up until now is if we wanted to write a string like x colon, and then in this example it's, x plus 1 is what we were doing. The way we did this with an f string was like this, and these are equivalent, right? So what we're seeing in here is equivalent to this, although actually I have a bug here, right? I needed to do stir if I wanted this to work out actually, right? So with an f string, you have the ability to substitute values, and those values are expressions. Typically, you're not going to do arithmetic in these, so typically it would be more common to just have something like, this, right? And this would have printed, in either case, x colon 1, and this is just a string. All right. Great questions on this. We'll get more practice with f strings. They are super handy. All right, all right. All right, we're going to jump right into one of the diagrams that we left off on. This one doesn't include f strings, but if you want to, after you evaluate this, you want to imagine what this would look like if you could use if we did use f strings here. That's a good little exercise. But let's try diagramming this and spend about 5-6 minutes on it. I might give one to that side.
He's a cute man. I hate how expensive these are.
I'm scared to hold them. I'm scared to accidentally talk into it.
You have to really try. You gotta go. This side. Just. Why don't you go to the resume reboot?
I don't want to go there because they're just gonna bully me about how I don't have any projects.
Nobody cares about projects. Yeah, like it's always the smart people who are incredibly capable. See, when I look at that, go, remember that these microphones are $600. Like, can you?
I think usually no, but I think.
Are you going to TA basketball sometime?
Is it a performance?
I think I'll finally go this year, even though I'm absolute trash at basketball.
You have to send in like.
Because at least you're taller.
Yeah, I'm just gonna lay it up the whole time.
It was really cool.
I'm about to commit some egregious fouls.
We should though. Not gonna call it though. We're gonna be like the Georgia Tech rep.
You know, we had to lose one at some point, better now than
We did have a
on Saturday. I'm gonna ask Chris if he's coming to basketball.
Is he going to game night tonight?
Yeah.
Okay, good.
Chris is nasty at basketball.
That doesn't surprise me at all.
Well,
Huh?
I'm gonna be in Nashville.
I don't know. I mean, for the game.
Oh yeah, I was watching it with Matt Bailey. Because Matt hates me.
It's like none of it. I know.
Stop.
Louis seems like he would go to every single basketball game.
He did. Vivian, Olivia, Megan, like all of the other TAs got it. Except Matt Bailey. Maddie got it. Give me a fucking break.
I say I hit the jackpot last year, so I wasn't expecting to get it. They're the people that like brought me stuff while I was in line, got tickets, and I was like, that's good karma. In reality, I could have just left and come back. Like everyone pretty much respected the workers.
Yeah. Nice to the Cole got traded for.
I'm so happy.
Yeah, I didn't want him.
You know,
I mean, he didn't get traded for by us.
no, true. No. I like them. So I was happy with that.
When I go from
I'm sad to see.
Pong to back, I'm confused on like where my return address is.
No, the Hurricanes aren't gonna.
So return address is wherever your function
Such an expiring contract.
So that's
On this, 2 more minutes.
we start with.
I also have him on my fantasy team, and he's about to produce way more.
You gotta wonder if the Hurricanes aren't gonna re-sign because he got like 12.
So yes, is wherever your function is called. So wherever you saw that
It's not gonna be
call
Jordan.
to palms, like at the first case, it's
Put
at
him on the like not too much.
then
You never know. Somebody could offer sheet him.
And then
He's a fan. He's a fan.
exactly. That's where it was called.
They offer sheet him. Like, I doubt we match him. And a lot of teams are desperate for young talent after hockey players finally got a back. The section's involved.
Yeah, maybe.
Sorry, allegedly.
Maybe
They
he'll
definitely
go
have.
to Jersey.
I love how everybody's using this allegedly, but like, let's all be honest for a second. They
Here's
definitely
the
did
thing.
it.
They definitely did it. Like it definitely happened. I think the case is gonna be to the second place. That's it. I don't think anyone's gonna deny that it happened.
I mean, it definitely was. solve. They basically, like, one dude got this girl really drunk and hooked up with her, and then got her even more drunk and invited his friend.
Oh yeah.
20 more seconds. 20 more seconds.
Rip the Flyers. They needed
Yeah, Carter Hart.
It was Carter Hart. It was.
He belongs there. He's a
Was it?
dickhead.
Was it 2 from Jersey?
Yeah, it was 2 from Jersey,
Which no surprise there.
which it was the 2 from Jersey and Carter Hart were the big profile ones. I think there was like 1 from Ottawa or something. There were 5. There were 5 total.
There is one from.
And there's like no time to do it.
I have a great feel about it.
Wait, do not throw at people.
All right.
Shitty organization.
Let's talk through this one. So we've got something kind of fun happening here. We've got a function ping. You'll notice that somewhere in its body it contains a function call to the function named pong. We get function pong, and inside of its body it contains a function call to the function named ping. So these functions are calling each other back and forth in some pattern. We also have here an if-then-else statement, and notice that we do have an else here. So just as a quick review, when we have an if statement, if that condition is true, we would go to line 6, return I. If I less than equal to 0 is false, we would go to the else and return the result of calling the pong function. So I've gone ahead and fast forwarded to the point of line 17 where we reach the print statement that's kicking off some process, and ping is being evaluated with I is assigned 2 as the argument for I. So I've gone ahead and set up that frame. We jump right in, and the very first thing that we see printed is ping concatenated with stir I. I's value in the current frame is 2, right? Because we just talked about f strings, and this is a great example, I'm going to pause right here just to say this string could have been, this print statement could have been rewritten as print f string ping colon and then curly brace I colon, or sorry, curly brace quotation, right? And so that would have been the exact same output. But for now, we're using just the old school, what we had seen before, print statement. Then we reach line 6, and we evaluate is I less than or equal to 0. Well, I in our current frame is 2, so this is false, right? And this is what leads us to line 9, where we reach a return statement. But that return statement, we need to go evaluate the result of calling the function pong. And here we're calling pong. We're saying that the argument I is going to be I's current value minus 1. So when we evaluate, this is the same as saying we're trying to call pong. I is 1, right? So how do we evaluate that? Well, we add a new frame to our stack. We're going to call pong. The return address is going to be line 9, right? This is where the call evaluated. And our value for I is going to be 1, right? Now that we've set up this frame, we're going to jump into pong, and I'll continue here in just a moment, but any questions on what we've seen up until this point to get here? All right, so we reach this print statement, and we need to evaluate its contents, and so it's just pong. We look up what is stir I. Well, here's where our name resolution rules become very important, right? We've actually got 2 values of I in our stack. Which one are we talking about? Well, we're talking about our current frame. And remember, our current frame is the lowest frame on our stack, which is yet to return. So we're in the pong function, we're evaluating it. So the I that we care about is the value 1. So this would print out pong colon 1. And then we reach a return statement, but that has an expression. We've got another function call, right? So we know with function calls, we need to evaluate the arguments first. And remember that this is effectively the same as saying, ping. I is currently 1, so I is 0 for this next frame, all right? So we need to evaluate this function call. Whenever we reach a function call, we always do the same set of steps. We set up a new frame for it. Ping. The return address this time around is line 14. This is the line that we've been working on, right? And I is 0 here, right? Before I jump into back up to ping, right, before I go back up to line 5 and continue here, any questions on this sequence of steps? Right, so yeah, good. Great, why are the print functions above the return or very first? So when it comes to differentiating between print and return, the way I like to think about it is printing is for humans. That's what's going to send output to our screen. So if we ran this, all of what we're seeing in the environment diagram is happening inside of our computer. But what we would actually see show up on our screens is what's in this output column. And so the reason why we put these print statements in here in this way is we're just trying to give ourselves a sense of in what order and what values of I did these function calls evaluate, right? If we didn't have either of those print statements, then all we would see is whatever, we still don't know what we're going to see. We haven't gotten there yet, but what happens on line 17. The last thing I'll mention is if we had our print statements after our returns, we wouldn't see anything because as soon as we reach one of those return statements, we're not going to do anything else that follows that in that particular function call. That'll be the last thing we do for a particular function call. That's a great question, though. Other questions? All right, and TAs, if I'm missing any hands anywhere, do flag me. All right, so we've jumped to line 5. We're back in ping. Notice, though, that on our current frame, the lowest on the stack that's yet to return, I's value is 0. So now when we reach this line 5 again, our output's going to be different. We're going to print ping : 0, right? Because I in our current frame is 0, even though now we've got 3 values of I residing in memory, right? And 2 frames for ping residing in memory. The current one we're working on is the lowest one that hasn't returned. All right, so now we test. Is I less than or equal to 0? True or false? True, right? So I is currently 0. 0 less than or equal to 0, that's true. And so here we reach line 7, and we return I. So we look up what's I. Well, I is 0. So our return value for this frame is going to be 0, all right? In other words, we replace, we substitute, we read 0 here. And now we have the job of what do we do when a function returns? Well, we take that return value and we send it back to the line that the function call occurred on. In this case, we're in the frame where the return address is line 14, so we send 0 back to line 14. Right, so that's down here. This function called a ping. We now know that that resulted in a value of 0. But notice that our current frame, the lowest frame on the stack that is yet to return, well, this frame returned, so now we're back in this frame, right? And so now what we're saying is this return value is also going to be 0, right? This call to ping resulted in a value of 0, and we're going to return that result, so it's going to be 0. Right? But this time around, we're not returning, we have to look at, okay, for this frame, now that we've figured out where it's going to return, we're going to return to line 9, right? So if this was 0, and we're going to send that back to line 9, that was this call to pong, which is what got us into that frame, right? But now our lowest frame is this ping frame, where I was originally 2. This function call evaluated to 0. That's part of the return statement we were trying to keep track of. So now our return value for this frame is 0. But where do we send that return value back to? Well, we send it back to line 17, where this all started from, right? Way back down at the very beginning. So if I erase this. So now we're going to send this 0 back down to line 17. Ping I is assigned 2, resulted in a value of 0, and so at this point we would finally print out 0, and that print statement is completed, and our function in our program is done. Right? There are a few things that are interesting to notice here. First, we're seeing a call to ping lead to a call to pong, lead to a call to ping. But ultimately, in that third frame where I was 0, we reached a return statement that didn't involve another function call. So we started returning that value back to the function calls where it originated from. One of the reasons why these environment diagrams are so handy is notice that we've got values of I changing for each of these frames and keeping track of all those details and what was the function call that led to me being in this place of my evaluation. We can keep track of all that through our environment diagram. In other words, I want to just briefly trace at a high level. So if we zoom out a little bit, notice line 17, which was our first return address to ping, led us to ping. Then on line 9, which was our second return address, that led us to pong. Then on line 14, that was our third return address. That led us back into ping. And finally, we had a way of going back to where we came from. So we backtracked from here. So I'm going to draw this actually in green. So we went back to where we came from. That went back to where we came from. And ultimately, that's what led us there. So in just a very similar way to how if you climb a building of stairs, or let's say imagine you're starting on the top floor, right, of a building, and you work your way down. In this case, we're working our way down these frames on the stack. If you wanted to go back to where you started, you've got to work your way back up in the order in which you went there. These are all the rules that you already knew actually going into quiz 0 with the one caveat that in order for this type of a behavior to work, you have to have conditionals. So that's why we couldn't do this before the quiz. With that high-level explanation, I'm going to open it up for, oops, I didn't mean to do that, for questions. Let me just delete this real quick. Questions on this example? Yep.
Can you explain again how you got the return value for the first ping on with that? I understand the last ping's return value. Can you explain the zeros for the ping and the pong?
Can I explain the zeros for the ping and the pong? So when we are looking at this frame, right, what got us there was this function call, right? Ping I is I minus 1. In other words, this was the same as ping I is 0, right? Because in the frame of pong that we were calling it, I was currently 1. So when we went to evaluate this, this call, ping I 0 from the pong frame, that's what led us into ping, where I was 0, and in that case, we just returned 0 back, and that's straightforward. But notice, when we returned 0, oops, sorry, wrong place. When we returned 0 from here back to the call that led it there, this effectively became return 0, right? Because ping I is 0, evaluated to 0. That's what we learned with the last frame. And so now we reached on line 14 here. The evaluation of ping I is 0 is 0 itself, so we're going to return that 0 back to where we came from, which was line 9, right? And it keeps returning back to where the original call came from until we ultimately get to ping I is 2. And so it's almost as if these functions are asking each other one after the other, hey, what's your return value? And they're having to turn to the next function and say, what's your return value? Until they reach the end, and then they pass it back up the chain of how you got there. But they're going back and forth. And this has a technical term concept, which is mutual recursion. These functions are defined in terms of each other. Yep, question?
You do the return value and then you go to the next section or whatever, and then but with this one you just do the return value.
So the question is, when it comes to the return value, why is it sometimes you might continue on to the next line, versus jump back in the way that we did here. And the key rule and the key intuition of the return value, and I can try and on the next diagram that we do, I'll try and be very careful of saying this, is the only rule that you need to remember about return is when you reach a return statement, in your current frame, you're always going to send that value back to the return address. And so this is telling you what is the very next line that, or what is the line that this value is going to be sent to, right? And so notice each of these RAs is exactly, first we called ping on line 17, and then on line 9 we wound up calling pong, and then on line 14 we wound up calling ping. And then finally we reached return I, and that's what sent it back here, and then back here, and then back here. And it's those line numbers that we're keeping track of in the return address that you can think of as bookmarks. Like here's the place where I need to send my result back to. Here's the next place I need to return my result back to. And so the RA is where the return address is the line number that's keeping track of all of this. So in the examples that you're thinking of previously, in fact, maybe even, let's see if Keynote's going to maintain my annotations here. It's not. In this example, notice we had a very simple evaluation. So this is the first example we had. On line 15, we reached a function call we called foo. The return address was line 15. When we reached one of those return statements, we went back to line 15, and then we continued on to the next line. It's the same rule being applied. You're always going to take your result back to your return address or your RA, and that's why it's such an important thing to keep track of. This is just a more nuanced usage where we've got a more fascinating pattern of calls happening here. One of my challenge questions to you is what would happen if you called, instead of ping I is 2, ping I is 110? And hopefully you can believe and use some intuition that you get, ping 110, pong 109, ping 108, pong 107, and so on until you ultimately reach 0. And I can promise you we're never going to ask you to diagram something like that in class or on a quiz, but behind the scenes your computer would be doing that. There would be 110 frames that were evaluated in order to bring that together. Other questions on this? All right. This is mutual recursion, and that you all are able to trace through that, and this early in the class is really exciting. We're going to skip over that, and I want to talk about tuples. All right, so this is going to be a new concept, and tuples are going to give us a fixed length sequence of values. All right. So far, we've seen one sequence of values. Can anyone name a sequence of values that we've seen so far? A sequence is something that's in order and indexable and has a length. String, yes. So tuples are going to give us an alternate to a, so a string is sort of a sequence of characters, right? Tuples are a sequence of any values we'd like. And I want to show you two forms of a tuple. So first, we're going to start with, I actually think it makes sense to start with the value, example values. And then we'll talk about types, right? So the way that you specify a tuple value in Python is another usage of parentheses. So we're about to have 3 different uses of parentheses, and we should be careful to differentiate them. But if you put a parenthesis, and then for a single value tuple, you could do something like 1.0, and then a comma, and then a closing parenthesis. All right? But it's pretty uncommon to have a single value tuple. Like the whole point of a tuple is you want to have multiple values. Like we wanted an XY coordinate, right? So much more common would be an open parenthesis, 1.0, 2.0. Right? And that would be a tuple with 2 float values in it, 1.0 followed by 2.0. What's kind of neat about tuples is we can pass multiple values. Like maybe we wanted to keep track of someone's name and their age. You could have a tuple of a string, such as, you can write your own name here, Chris, and an age, and I am blundering my way into revealing this to you all, and an age, which I'll give an int. And so notice that we've got two different types here. Furthermore, if we wanted a 3D point, you could imagine 1.0, 2.0, 3.0. They don't have to be in order, so why don't I actually make this like 22.0? There's no implied order or anything like that, right? So these are our example values. And let's talk about types. So what if we wanted to write a function that took a tuple and that took any one of these kinds of tuples, like a tuple that had only one float as a part of it? Well, the type for this would be the lowercase word tuple, and then a square bracket, and float. Right? This is saying a tuple that has one float. As you can imagine, the type that you might write for the second is tuple float float. And this would specifically be any tuple value that has two floats in it. Right? You can trust your intuitions and how this works on the third example as well. This would be a tuple of type str and int. And on this very last example, I want to give you one more, because we're going to be using this, more generalized way of specifying a tuple, which is, let's say we wanted to say a tuple that has all the same types of values, so a tuple of many floats, but we don't actually care how many. This is going to be a function that works with a tuple of any length as long as they're all the same type. And so in that case, the final type example here I'll give you is tuple float and then ellipses. Right? So 3 dots. And so this is pretty cool. We're able to have a sequence of values represented as one thing. So we're about to see an example of this where we might have a function like def sum, and we might have the items specified as a tuple of floats. And we would expect this to return a float. So if we hallucinate, and I'm just going to put some dots for the implementation. If we hallucinate the signature of a function like sum, where you give me some numbers that we're going to call items, and what I want for those items is that to be a tuple of some sequence of floats, right? And what I'm going to give you back is the float that is the result of adding all these numbers in this tuple up. Notice we're able to have one parameter, or one value, that can contain a sequence of more values, and that's pretty cool, right? Let me pause right here for a moment and see if anyone has questions on tuples. Yep. So because most of the class doesn't have prior experience, I'm not going to address that head on, but what I'll say is these are immutable in that you can't change them. Once you have a tuple, you can't change anything about it. And that's a good thing for now. It makes our life a little bit simpler. You can make new tuples, right? You could say, okay, take this one tuple and let's make a new tuple based on that previous one. But they're fixed in their contents as well as their lengths. But you can access the values of a tuple using indexing. So somewhere in the sum function, we could say something like we've been able to do with strings, items and say like 0, and that would give us the first value of a tuple. Right? So once you have a name, like a variable name of a tuple, or a parameter name, I should say, then you can access it just like you could characters in a string using the indexing notation. Yep? Yes, great question. So the question is, if we write the return like this, does that mean we're going to get one single float back? Absolutely. So sum is a function that you give me a tuple of floats, and I'll give you one float back, which is adding them all up. Yep, great question. And that's the intuition, and that's important for, you can deduce that from looking at this type and have some faith and trust that you're going to get one float back. Yep. And a continuation of this question, which is fantastic, is if you wanted to write a function, sum wouldn't really make sense here, but if you wanted to write another function, such as maybe double every number in one tuple and produce a new tuple, could you have it return a tuple as well? And yeah, so anywhere you can use types like int, str, bool, and float, we can use tuple types as well. Yep, great question. There's another question over here, yep.
What's the difference between putting it in the tuple versus just
Great question. What's the difference between putting it in a tuple versus having many parameters? So what we're going to see is, one, we can have, thanks to this style of tuple and being able to say it's a tuple with at least one float. Well, I shouldn't even say at least one float, but we can think of it as at least one float, but any number of floats, is that we can have a varying lengths to these, and we can write more, like this sum function. If you needed to specify, sum with as many integers as you want, or floats as you wanted, you'd have a very long list of parameters, and you might not know. And so we're going to be able to write functions that start to you'll be able to give it a collection or a sequence of values. Who knows and hopefully cares how long it is, and we can do something meaningful with a larger set of data, such as add all those numbers up. It's a great question. There are some similarities between these two things, but we'll also see that this gives us a way of passing around a collection of values a little bit more nicely than having to have a bunch of individual parameters. I'm actually going to split this slide into two, and we're going to talk about built-in aggregation functions on this side in just a moment. I want to briefly just reemphasize something I said in the previous slide, which is, let's imagine we have a function that's like I said, def sum, and then a tuple. Let's call this, sorry, I got to give this parameter a name. Value items is what I called it before. And this is a tuple of floats. And it's going to return a float. To access items, you use the indexing notation of, say, items 0, which I mentioned before, but this continues on to items, and this would be length of items -1. So just like we saw with strings, we always start indexing of our sequences at 0, and then the maximum index of a tuple is going to be the length of that tuple -1 because we started from 0. It's just that off by 1 offset. And as you can kind of see here, I gave this away, but we can learn the number of items in a tuple with the len operator, or the len function, just like you've used before. And so I'll just make some notes: number of items and accessing. Right. Now, there are a few built-in functions that Python has. Turns out sum is one of them. So if we wouldn't have to write this function ourselves. We could have, if we had a tuple named, say, scores, we could have said sum scores. and gotten back a single value that is the sum of those scores, right? So add all items in a numeric sequence. Similarly, there are self-explanatory built-in aggregation functions like min and max, where these would find the largest and smallest items of a tuple respectively. Right? And that would be a tuple that contains all numbers. It turns out this would work with strings using string comparison, but typically you're going to use these with numerical values. Right? So these are built in, but one of the things I want to give you a little bit of intuition on and give you a chance to try imagining is how might we write, based on what we know so far, there are many ways of writing a sum function, but how might we write that and evaluate it? Right? Actually, for time purposes, I want to give you a chance to process this, and then we'll take questions on tuples at the end. So imagine this is your code snippet. I'm actually going to switch over to my example of this. All right, so imagine you've got this sum function, and it's defined as such. It's a little different than the one we were just looking at, but that's for our purposes of implementation and tracing this. And see if you can, with your neighbors, try tracing this function evaluation in a diagram. One thing I should mention, which we haven't talked about, and I wanted to make a note of this as you're getting into it, so hopefully you're with me, is how do we represent one of these tuples in memory, right? One valid way of doing this for tuples would be just to write it as you'd expect, but I want to give you a little bit of a preview and simplify your life so that you can just draw arrows here. And let's trace through this first function call together. So this first function call is going to be to sum, and we're going to have a return address of line 9. And here, we're going to say values. And rather than trying to write in the tuple as we have other values, this is going to be another place where we use the heap. All right, so I'm going to draw a line over to the heap, and I'm just going to have a tuple here as a heading. And index 0 is going to be 1.0, index 1 is going to be 2.0, and index 2 is going to be 3.0. All right, so we're going to make a little table here. And this makes things easier as we move along. Okay? And then we're going to have a value for I, that's 0, and a value for total. And we start our total at 0. As you can imagine, when you're adding things up, you tend to start from 0. So we've established this, and we're ready to jump into this function definition. So we jump in, and what happens? Well, on line 3, we ask, is I greater than or equal to the length of values? I is 0. The length of our values is actually 3, right? So len values would be 3. We have 3 items in this tuple. So no, this is false. And here we reach the function call on line 6. All right, I'm going to help you set up this function call as well, and then I'm going to turn it over to you all to try it on your own. All right, so when we reach line 6, wow, we've got a function call to the sum function from within the sum function. That's kind of mind-blowing and awesome. So what do? Well, we do the same things we always do with a function call. We add a frame for it, sum. This time around, the return address is line 6. What do we do with values here? So with values, what we tend to do is not make a whole copy, but just draw another arrow from values to this exact same tuple, right? We're not going to change anything about this tuple. We're referencing the same tuple, so we're just going to draw an arrow to it. And this is actually what would be happening under the hood in our machines. And then we're trying to set up, well, what is I going to be? Well, we need to evaluate I plus 1. I was previously 0, so I will be 1. And then what is total plus values I? So total is currently 0 in the frame we were at before, right? So what is 0 plus values I? Well, I is 0, so values at index 0, we look that up, and it's 1.0. So 0 plus 1.0 would be 1.0 for total. So I in this next frame would be 1, and total would be 1.0. All right? That's a brand new frame. And so from here, you would wind up going back to line 3, but notice that now our current frame is no longer the frame that is that we were in before. It's the lowest on our stack that's yet to return. So now we're in the frame where I is 1 and total is 1 and our return address is 6. The values are still the same. So I'm going to turn it over to you all to try and complete the diagram from here.
It's probably about the time that happens to my time. Yeah, actually, no. I only have one class that has tests, so that's kind of nice. No, no, I'm in 4, bitch. So yeah. My first exam is February 19th. Hold this.
Hold it. There's the table. Hi, Josh. I'm not giving.
What is total equals total values I plus total plus values I mean? What is the values I plus values I referring to?
So you can index the tuples. So the I, you see I equals 0 down in the first function call.
Oh, and then that is
means
y
it's,
equals
so it's going to be values I is going to equal total, right? Like I'm trying to look at the.
So you use I as the index within.
Yeah. In this case, it doesn't actually go to. It doesn't actually clock that.
And in the next one, I is going to be when you index your tuples.
Yeah. Like I've made a plate. You call it with I equals I plus 1.
That's so litty. Thank you.
If you did that, then it would you just be doing the 1.0. Yeah. Pretty sure that's not what it doesn't. The I that's in the value. So I is equal to 0. So values, and then I is
Week 3. I know. I like this way better than I feel bad for the TAs that had to read Charcoal. Yeah.
It's so awful.
It is awful.
Yeah. So 1 plus 1 plus 1 will be 2. Yeah. And then same thing, it's 2 greater than values. How many values?
2 more minutes on this. 2 more minutes.
The length of value you have. Yes. So when it gets to the third cycle, it'll stop, right? Yeah. It's greater than equal. Yeah. It'll be with values. Of values. Because you didn't. Oh, because you haven't added. No, it's 3 actually. You just add the 1 plus 2. Yeah, exactly. So right here for the total, I'm just putting like on that second, on that second time when I equals 2, right? Yeah. It's evaluating totals as, or like total equals total plus values 1, right? Yeah. And not 2, even though I equals 2 at that time. Yeah. So like it doesn't actually clock that I is 2. What's the next?
One more minute. One more minute. All right. How many of you feel like your brain is finally awake this morning? Dang. Not many of you. All right, so this is true recursion. This is the idea where a function is defined in terms of itself, right? And here, sum is defined as a simple, cute little if-then-else statement, where in one case we're done, right? When we've run out of values to try and add to our sum, then what the result is what we've totaled up. It's like we're tallying up the values as we move through our tuple, right? Now I wanted to give you all a chance to process this before really breaking down the syntax, but in order to not skip over anything, notice that here's our values parameter, and we talked about the syntax of a tuple, and of course this is a tuple. It's the values surrounded by parentheses. And notice that we could have had more values here. We could have had comma 4, comma 5, comma 110, whatever. And that all will feed into the single parameter of values. And that's pretty cool. That's one of the big wins of having these types of sequences. All right? So we've paused execution. Our current frame is the frame where our return address is 6, i's value is 1, and the total, what we've added up so far is 1, right? We already added up index 0, that's 1.0. Now we're on index 1. What do we do next? Well, we test is I. So we look up what's I. I's current value is 1, right? So is 1 greater than or equal to the length of our values? We know that the length of our values is 3, so that's false. So we go to the return statement. We go to the else statement. Sorry, we go to the else statement, and it has a return statement, and that's another function call. And here we're adding another frame. But before we do that, we should, values is going to be the same. So we know that values is ultimately going to be an arrow to this tuple. But let's go ahead and figure out our other arguments. So I plus 1, I in our current frame is 1. So I in the next frame is going to be 2. And total is total plus values of index I. So I in our current frame is 1. Values of index 1 is 2.0, right? And our current total is 1.0 in our frame. So our next total is going to be the result of this, 3.0, right? So now that we've evaluated our arguments, we're ready to set up the frame for the next call. So we do that. I'm going to add a frame here. Sum, return address, line 6, and values is still the same. Nothing's changed. It's that same set of values. But this time around, I we just established is going to be 2, and total is going to be 3.0, right? That's what we calculated for each of those arguments. All right? I'll make this just a little bit smaller. And now we've established this new frame, and we're ready to, I'm going to move my dot here for keeping track of what is our current frame. It's the lowest frame on the stack yet to return. In other words, the lowest frame without an RV, and so now that frame is going to be here, but we've just established we're back up to line 3, so we've kind of looped back up in a sense. Before I continue on from here, any questions on what we've seen so far. Yep.
I thought when we were indexing, we needed to start from 0. So I'm a little bit confused as to why 0 equals 0 and we went to 1.
Great. So the piece that's the sort of fragile dance here is when we evaluate this line, and we're actually going to do this one more time. So I might actually try and answer your question in just one moment when we get there this next time, because we're about to get there one more time. Yeah, question. How do we calculate the length of the values to be 3? Great question. So we look at values, and we see that it's this tuple, and we can count up 1, 2, 3 at indices 0, 1, 2. We could have also looked at the original starting value and seen that there were 3 float values in that. And so the length of a tuple is the number of items it contains. Great question. All right, so let me get back to the previous question, and we'll get there as soon as we get to this evaluation. And we're almost done with this one. It goes very quickly once we're returning, right? So is 2, which is our current value of I, greater than or equal to the length of our values, which is 3? No, we're still not there yet. So we once again reach line 6. That's our else branch. And we're trying to return the sum of these values. All right? And so here, I want to, before we even go, like we're about to set up this frame for sum, right? But this very good question of what's going on with these indices and I. This is important to pause, right? We've yet to change frames. We're still in the frame where I is 2 and total is 3. Before we go to the next frame, right, before we set up this one that I've just added, remember the first step that we need to take care of is fully evaluating the expressions of the arguments, right? And so values we know is going to be the same. Values aren't changing. Values are ultimately going to be that tuple. But let's be very careful here, right? I'm actually going to, so here, notice we're saying in the next frame, I is going to be I's current value plus 1, right? So in our current frame, I is 2. In other words, 2 plus 1 is going to be, 3. So I is 3, and then total is going to be the current total, which is 3.0, plus values of our current value of I, right? So our current value of I is 2 in that frame. And this is the piece where I think you may have been feeling like, wait, are we in the next frame or are we in the current frame? So when we're setting up this call, we first have to figure out what are these argument values for the next frame going to be, but we're still using the current ones, right? So I was 2, so now we're going to say, well, the total in the next frame that we're about to fill in is going to be 3.0, our current total plus values at index 2. So we look in our table, what's values at index 2? That's 3.0 here, right? So 3.0 plus 3.0 is going to be the same as saying total of 6.0. And now we've got all our values ready to set up the final frame here. So we go here and we say that our return address is line 6, and our values is still the same, right? But I is now going to be 3, right? That's what we just calculated. And total is going to be 6. Right? So that's how we got into this. And now we've got 1 minute to work our way back, right? So we jump in and we see that I is currently 3. So is 3 greater than or equal to the length of values? Yes, that's true. And here, finally, wow, after all that work, we've reached return total. So we look at what is total. Total is 6.0, right? This is the total of adding up 1 plus 2 plus 3. And so now our return value is going to be 6.0. And here's where things are very fun. What do we do with this 6.0? We send it back to line 6. That's the same line we're on, right? That's funny. But notice that our frame has changed. We're no longer in the frame we were before. We're in this frame. But we've just returned 6 as the calculation of this. So this frame is also going to return 6. There's nothing more for us to do. And that's returning it back to line 6. Well, that's all we needed to do again. So this is also going to return 6. And that's returning it back to line 6. That's the same line we're on. That's also going to return 6. And finally, this is returning it back to line 9, which is where we started, and the output would be 6.0. And that's how we would add up 1 plus 2 plus 3. That's all I got for today. We'll be spending some more time with recursion. The next exercise will be out soon.
Is it stated in the syllabus that if you do well enough, like you had a score better than your lowest score,
It'll replace it. Yep. Yep. Thank you.